Thank you. Very good morning. Thank you for being here in this presentation. I'm going to talk about my thesis work titled Towards a Multimodal Knowledge Base for Indian Art Music, a case study with melodic intonation. Before I begin the presentation, I'd like to thank Chavia for giving me this opportunity to work in the CompMusic project, and I would like to thank jury members for critically reading the document and being here today. So let's start with maybe broad outline of this presentation. So it has three parts. I kept it simple deliberately, and by the end of the first part, we would know what this work is about and why it is necessary in this context and how we went about it. So let's deconstruct the title bit and understand the context of the work. In simplest of the terms, a knowledge base can be defined as structured information represented using an object model with class hierarchy and relationships therein. And this object model is what we meant by ontology. And you can think of an ontology as an enriched schema that can be used to encode knowledge about a given concept. And by multimodal, we mean different sources of data, different types of data that we work with, including audio, scores, symbolic notations, and music context data, which mainly include lyrics, metadata, and the musicological knowledge. And of course, the user context data, which includes the social networks, the user preferences, and their current mood and activity, and so on and so forth. But in this context of this thesis, we would focus on two of these modalities, which include mainly the audio data and the music context data. So basically, these sources include the audio music recordings and the features that we extract from them, musicological knowledge, and metadata and unstructured text. So combining these both, a multimodal knowledge base is achieved when we extract information, musically meaningful information from these sources and structure it using ontologies. And for this task, we have chosen Indian art music with two primary reasons. It's one of the most well-explored musicological tradition in the world, and the musicological literature available, it spans more than a millennia. And especially as the conceptualization of the music is very different from popular Western music styles, it poses new challenges. And within Indian art music tradition, we chose to work on melodic intonation, and that's within the context of CompMusic project, it complements pretty much the work that is going on in other melodic aspects of Indian art music, which are melodic motifs and tonic. And we said towards because it's a gigantic work, and this is just a narrow topic that we picked to make a headway in this direction. And we need similar parallel work with each of the musical concept in this tradition to make it a more complete knowledge base. And also because the data sources that we consider, audio, metadata, and musicological knowledge, are a few of the many data sources that we have shown. And as we mentioned, multimodality of music data sources is one of the primary driving motivation of this work, and closely linked is this aspect of maximizing the impact of using these multimodal data sources in our day-to-day work. And in our humble opinion, that's possible in a sustainable manner with having a knowledge representation framework and reducing high-level abstracted information from these different multimodal data sources and structuring it using this knowledge representation framework. And in line with this, we have 4 concrete objectives in the thesis. The first one is developing and creating ontologies for Carnatic music with a specific emphasis on melodic aspects. And this will be our knowledge representation framework. And the second one is to develop a representation for melodic intonation from audio music recordings. And with an emphasis on the fact that it has to facilitate high-level abstraction of this intonation description to be able to represent using the ontologies. And the third objective is extracting concepts and relations from unstructured text. And this we propose to do using state-of-the-art information extraction systems. And in this presentation, we will not be covering this aspect. And finally, have a knowledge base with all the different information that we extracted and retrieved from various modalities. And with that, I hope you get a sense of what this work is about and why we went about it and how did we plan to achieve it. And this is the starting of the second part. And here we deal with getting a representation for melodic intonation from audio music recordings, and we would like to answer these questions by the end of the that part. So basically, it's what's our representation to capture melodic intonation, how did we create it, and how did we test it. So we would require some musical background. So I'll be starting with giving few definitions here and there, and then we'll start with pitch histograms, using pitch histograms to get us for a description, and we would point out the problems and the limitations there, and we would propose approaches step by step, improving the baseline representation that we developed, and then finally qualitatively and quantitatively evaluate that representation. By qualitatively, I mean it should be musically valid. So Carnatic music is a South Indian art music tradition. It's an oral tradition, and with a primary focus on improvisation. And a typical ensemble setup is something like what is shown there, with the lead musician sitting at the center, and primary melodic accompaniment on this side, and primary rhythmic accompaniment on that side. And you have more rhythmic accompaniment sitting on the back with a drone. So, like I said, I have listed, in fact, many of the core references that the thesis reads and refers to many of the musical concepts that we described. And one of the main core the reference is this one, the Sangeeta Sampradaya Pradarshini, which is pretty much the Bible for music concepts for contemporary Carnatic music. And besides referring to this literature, we also worked closely with many musicians. In fact, Vignesh Ishwar there is a master student from SMC, and and his guru T.M. Krishna is also one of the closest collaborators. He is a leading Carnatic vocalist today, and Sir N. Ramanathan is a very well-known and accepted Carnatic musicologist. So let's listen how this music sounds like. That would go on, the initial melodic phrase will be explored with several melodic variations, and then it would settle on to the initial pallavi, what they call it. And so these are the concepts that we keep coming back to throughout the thesis. I would define them at one place here. So a raga can be understood as a melodic framework similar to a mode that defines a set of rules for creating melodies. And swara, it plays a similar role to that of a note in Western classical music, but conceptually it's very different. And these are the symbols that we use to represent swaras, which is similar to solfege in Western classical music. And with gamaka, together with gamaka, swara plays this role of atomic unit in Carnatic music. And we can't separate them and say that swara is an atomic unit and gamaka is another one, but they coalesce and form one single melodic atomic unit. And basically, gamaka is this class of melodic movements, very short melodic movements that give this flavor to a raga. So, and forms we define when we refer to them. And these are two types of ragas that we also refer extensively in this work. Allied ragas are those ragas which share the same set of swaras but are characteristically entirely different because of the permissible usage of these swaras, the role these swaras play in the raga. So basically they just share the same scalar structure. And phraseology-based ragas are those which have organically inherited a pool of these musical characteristics and not scale-based ragas. So let's understand what's intonation, what we meant by intonation. So in the context of Indian art music, we define melodic intonation as characteristics of pitches and pitch modulations used by an artist in a performance. So let's quickly listen to two audio samples that will make it very clear why we defined it that way. So these are two swaras, same swaras, sung in two different ragas. So the swara is ma, and this is how it's sung in Saveri.
Ma, ma,
And the plot corresponds to tonic normalized version of the same. And this is how Begada ma sounds like.
ma, ma, ma.
So as you can see that it's the same swara, but it's completely differently articulated in these two different ragas. This is what we mean when we say characteristics of these pitches and pitch modulations used in a specific context. So, and by now it should be clear that how it is different from tuning. Tuning is where we specifies a set of intervals that are used to tune an instrument, whereas intonation refers to the actual performance and the pitches used therein. So let's start with understanding the work on pitch histograms and in understanding melodic intonation. So by pitch histograms, we mean it's a summary view of melodic contour showing relative uses of pitches in the performance. And these are example plots of two different ragas that show relative usage of their pitches. So in all the plots of this work, the x-axis refers to cents and the y-axis is basically a normalized count of those histogram values. So in the we consolidated the past work that takes pitch histograms and works with intonation and tuning related aspects. And basically they fall into three categories. The first category is they pick the peaks from pitch histograms and use that to match scales between ragas. And that's the simplest approach. And the second approach is where they discard the transitory movements and only consider the steady regions in the contour and build a pitch class profile out of them. So pitch class profile is basically a count of each of the pitch, how many times each of the pitch classes occurs in the whole pitch contour. And it can be weighted by the duration of the steady region or the number of such steady regions. And pitch class, last term is using pitch class distribution from the whole pitch contour. And this is where, and this is used in both Turkish makam music and Indian ragas with a good success. So these methods and approaches have been proposed over diverse data sets, and to get started with our work, we evaluated all of them on a common data set which is drawn from CompMusic corpus. So these are different variations of the data set. So in the first one, we have specifically collected ragas which are scale based, so that these methods are evaluated on using scales. And for these approaches, we have varied the recordings per raga and the total number of ragas and created 3 different data sets for each of the Carnatic and Hindustani music. And with all the parameters and number of experiments, so it comes down to 670 experiments between these 3. And I'll just summarize what's the takeaway from this evaluation. So it seems like the pitch class profiles, which are weighted by the duration of study regions, are the ones that performed best among the 3. The pitch class profiles weighted by the instance, and the other one is the continuous pitch contour. So this came as a surprise for us because the first result is expected, that weighting by study regions, weighting by duration is expected, but the second result is somewhat perplexing because we expect that the complete pitch contour without discarding the transitory movements is what should be characterizing more the ragas and not the flat study regions. And so this experiment is published in JNMR 2012. And like I said, our hypothesis is that these transitory movements and gamakas used on the ragas, they pretty much influence the pitch distribution in the histogram. So we started another experiment where we discard the previous parameterization or previous representation of pitch histogram and start looking at in a new way. And here we take audio and segment it into vocal, violin, and percussion segments. The reason we do it is that the sources of intonation are varied and they are not tested well. So there is a hypothesis that between 2 singers, the intonation of the same swara in the same raga can vary. And we did not know when we started this work how much this matters. So we just segmented the vocal regions that are of the lead singer and just used those. And for this, we annotated 300 minutes of data between these classes and thoroughly tested several sets of features and finally obtained this accuracy. And the next step is predominant melody extraction and audio and then tonic normalization. We used a Melodia proposed by Salomon and Gomez because that's the method at that time that was proved to be the state of the art, especially for music such as this one, in a heterophonic context. And we used a tonic identification approach proposed by Gulati, and both these implementations are obtained from Essentia, audio library from MTG. And then we compute histogram and then detect peaks. For peaks, we have a combinations of many constraints and then many approaches. And what we did is grid search with the labeled data and obtained best combination of the approach and the constraints. And that gave us 97% of accuracy. So, and the next step, once we have the peaks, is to determine the bounds of the peak. And this is very tricky. And we had to take a musicologically invalid decision, let's say, but there doesn't seem to be any other way in this scenario. So what we did was to get the valley next to the peak and see if it is within 50 cents region. And the reason we considered 50 cents is that this semitonal distance is often close to 100 cents. And so if it is less than 50 cents, we use the valley point. Otherwise, we use a hard bound of 50 cents. And as we would see, this is a little detrimental to this method. And from the distribution that we isolate, we extract these parameters, which are peak location, normalized amplitude, and different properties of the distribution. Basically, these properties, they characterize the shape of the distribution, like how spread it is, and how asymmetric, and then how tailed the distribution looks like. So we expect that these shape parameters contain some information on how the melodic movements are influencing the distribution around the peak. And we have done this in 3 octaves across all the 12 swaras, and there are 6 parameters per swara. That comes to around 216 parameters. And for evaluation, we have considered baseline to be the pitch class profile weighted by duration. And we have conducted two tests. First one is feature selection test and the other one is classification of ragas. The reason behind choosing feature selection is that we would like to know what's the information content in these new features. Are they qualified enough, or are they rich enough that they are chosen more frequently or more commonly than the established parameters. So these are result tables. In this table, the OCC refers to average number of times a feature is picked per recording. So since we picked five features out of 216 in every run, this should be the maximum of 5. And the REC is the ratio of recordings where a feature is picked to total number of recordings. So the maximum should be 1. And going by that, these features are decently picked. I mean, there are at least 40% of the cases where most of these features are picked. However, position and amplitude, which are from the previous state of the art, those are the most preferred ones. Besides them, the mean is something that's as preferred as the old parameters. Yeah. But yeah, I mean, having information content is one thing, but is that information content complementary enough for improving the results of raga classification is a completely different thing. So here we conduct classification experiments, and we found the differences are not that different, and whatever differences exist in allied ragas, even that is a thin margin. So, so the new parameters seem to be useful, but are not better than the existing state of the art. And the clear shortcomings of this method is that the pitches, no matter where they are sung, without regarding their melodic context, they are distributed across swaras. So this is closely tied to the loss of melodic and temporal context. For instance, here this is the ma that we have heard of Begada Raga, and despite this corresponding to this particular interval, all these pitches will go to other swaras in an aggregate pitch histogram based approach. So, and another musicologically invalid decision that we talked about is this hard bound on distributions. So clearly there are several issues with this method, and that's where we propose a new approach to handle some of these things. So clearly no hard bound on distributions, and then the new method should be able to allot all these transitory pitch values to the respective swara distribution. And then another clear objective that we defined in the beginning is to have a high-level abstraction that should be extractable from this representation. So we began looking at different classes of melodic movements that exist in this music, and these are what are summarized by Krishnaswamy. And of these classes, there seem to be two broad classes of melodic movements. The first class is oscillation, like this one and this one, and the other classes correspond to these kind of movements where the movement is based off on a swara and touches other swara on top of it or beneath it. So considering that, we have devised like an approach for segmenting the whole pitch contour and trying to get an estimate of melodic context of each of these small segments in the contour. So the approach is basically, it considers a given segment, and so each segment is contained within different windows. So for example, this segment here is contained in 5 different windows, starting from window 1 to window 4 different windows. And the idea is to summarize these windows in a way that is musically meaningful, and then estimate what swara is being sung at this particular segment. So, and an important factor in this particular approach is the duration of the melodic context that we consider around a particular segment. And we have a data set which we annotated that I'll talk about, and from that data set, we have estimated that average duration a swara is sung is around 200 to 250 milliseconds. And that means that the window, if it is less than 100 milliseconds, it gives rise to one particular context where the context I consider for the segment is approximately 1 swara duration. And a window which is greater than 100 milliseconds gives rise to another context wherein the segment is now, for the segment we are now considering multiple swaras. So let's take the two cases, one after the another. And in the first case, since the context we consider is of 1 swara duration, there are perceptual studies in Carnatic music that say that within a swara, the mean is what we perceive more or less of the movement. So we have decided to take that into account, and then, so a window is basically summarized by a mean. And then the next step would be we have a set of mean values for a segment, and then to get an estimate of what swara is being sung there. So here we chose median of these mean values for two reasons, because like we saw, the movements involved extreme peaks which are not that relevant, but most of the pitches are distributed where the movement is being based off. So a median downplays these extreme inflection points, and the next step we did is to quantize this median to fixed set of intervals that will remove the distributedness of this approach. So we just formalize this method. So each segment will be of the length of hop duration, and we define the segment using both window duration and hop duration. And then we get the mean values of the windows that engulf segment, and the total number of windows is basically the window length divided by the hop length. And then we get all the median of all the segments, and then distribute the pitch for each of these swaras. So again, we ran the same set of experiments on this approach, namely the feature selection method and the raga classification method. So we can see that clearly the number of times these features are now picked are much more than what we previously saw. And the relevance of position parameter also went down significantly. So, and we now see a noticeable margin in classification results, especially between in the case of all ragas where histogram peak parameterization performed a little context-based approach performed a little better than the previous one. And in the case of allied ragas, we did not notice a lot of difference. I think we know the reason. In the previous case, we were considering 3-class experiments, and here we were doing 2-class experiments because the number of allied ragas is not that huge. And this result is published in GNMR along with the histogram-based approaches. So to summarize that, this new approach has meant that the new parameters are selected a bit more often, but classification results also improved by a noticeable margin. However, there are a few shortcomings and few unknowns in the approach still. A clear shortcoming is the subdued presence of other swaras. So since we are considering the context of one swara, that did not leave us much into taking into account the influence of other swaras, neighboring swaras, and the transitory movements. So we were basically considering the movements within a swara duration. And we think it is important to consider the influence of other swaras, which will be accounted in the next approach. And one of the unknowns in this method is if it is detailed enough to scale to many ragas. In our database, we have, in our corpus, we have 161 ragas of Carnatic, and clearly it should, this representation should be tested to make sure that it scales to so many ragas. And another important thing is to validate if it is musically accurate. For any higher level abstraction of information from these, the abstraction should be musically meaningful to be represented using ontologies. So we now go to the next case where the context of this, for context considered for a segment is greater than one swara. And here we cannot clearly summarize the window using a mean value since there are multiple swaras. So we consider the most common pitch value, which is the dominant swara, or if there are two competing values, we consider a mean of that. The reason for doing the second one, which is considering a mean, is the Carnatic music is very replete with this particular kind of movement called kampita, which is a long oscillation which spans multiple swaras. And in those cases, the general intention of the swara being sung is the mean value of the whole oscillation. And we keep the median statistic. And another aspect that was a problem in the previous approach is that these pitch values, despite quantizing the median value to the nearest swara position, we still see a lot of distribution to swara places which are not found in raga. So we just restrict the distributions to those swaras which exist in the raga. So in order to test whether the representation scales, now we use a larger data set which has 40 ragas and 480 recordings, and especially considering it has 311 compositions, it's a pretty diverse data set. And to our knowledge, this is the largest data set for Carnatic music created until now. And this is first reported by Gulati. So we did a raga classification experiment with all the ragas using both histogram peak parameterization and context-based pitch distributions, and the results clearly indicate that this approach is statistically significant. The improvement is statistically significant than the previous one. And another aspect is, so one aspect is that we tested the parameters, but the representation itself needs to be tested. And so we directly compared the aggregate histograms and the individual swara histograms and did another run of raga classification. And here we see that aggregate histograms are not far behind the context-based swara distributions. And this clearly for us indicates the problem with the way we look at the aggregate histograms. So in this particular work, we addressed the lack of melodic and temporal context and handled some of the problems that we listed in the previous chapter. And this unknown, I think, is now, it's safe to say that we have a scalable representation that gives us approximately 86% of accuracy with 40 classes. And there is still this unknown, which is to ask if this representation is musically accurate. And that brings us to the last section of this part, where we qualitatively and quantitatively validate this representation. How much time do I have? Okay. 30 minutes. Okay. So for this, for validating it musically, we need a gold standard, and it's impossible to annotate manually the swaras in a pitch contour because of these complex melodic movements. And like I said, a swara and gamaka together form a melodic unit, and it's difficult even for a musician by looking at contour and demarcating the exact boundaries of these swaras. So we had to take an approach that leaves us with some ground truth. So Varnams are particular form in Carnatic music that are replete with raga characteristics and their phrases and movements. Basically, students learn these varnams at an early stage to get a hang of the raga. So, and they're sung in a given structure, more or less, without much improvisation. That gives a scope for semi-structured, semi-automatic alignment of notation and the score. So this is the data set with 7 ragas, and each raga has one composition being sung by at most 5 artists and at least 3. And all of these are monophonic recordings, and they are annotated at cycle level for rhythmic information. And we converted a few of the notations, symbolic notations, to machine readable format, in our case YAML. And we made a big assumption that within each annotated rhythmic cycle, the swaras are sung for equal duration amount of time. So, and we validate that assumption before using this data. So these are the examples of the swara plots that we obtain after extracting the pitch contours of each of the swaras. And like we said, with this assumption, it is possible that these plots are showing either the gamaka movements or the transitory movements. So it's bad if it shows transitory movements, because that could be because of our assumption that swaras are of equal length. And to validate that, we took out transition matrices of each of the swara in these set of ragas, and then plotted them to verify if we get any transitory movements into the plots. So basically here we see Begada, which is a flat ga, the swara is flat ga, and despite the fact that it shares more transitions to Re and Ma than Abogi, we don't see any of the transitions in the plot. And we saw similar pattern across all the swaras in the data set. So that gives us confirmation or validation that the assumption is safe enough. So yeah, and we can already see from these plots that we can make various inferences just by extracting some information of these plots. For example, Begada it's very clear, it's a single peak, and we can clearly say it's a steady swara. And with Abogi, with 2 peaks and no peak at the ga, we can clearly say it's an oscillation between the neighboring swaras. So things like this are now in sight. And Varnam dataset is quite useful in this sense, but it's quite limited too, because there are not many Varnams per raga in Carnatic music, and we have just recorded one composition per raga. So we parallelly collected another dataset called Kriti dataset. Kriti is the most sung form in Carnatic music. But the problem here is for annotations, it's coalesced with improvisations throughout the performance. And it's impossible to semi-automate these semi-manually annotate the tala cycles, which can be aligned with the symbolic notations. Indeed, we have notations converted to machine-readable format here too. And like I said, it's much more diverse than Varnam dataset. And this has 6 ragas, and we have 45 recordings from 30 compositions. And so we used an audio score alignment approach to partially align some of the instances in the performances with the symbolic notation, so that we get some ground truth from the Kriti dataset. But of course, it's quite challenging because of this improvisatory aspect. You cannot align the entire recording to a musical notation. And so we adopted a partial alignment approach proposed by Satan and Sarra. And this is basically a summary of these steps. We extract predominant melody, normalize using tonic from the audio, and then synthesize a pitch contour from the notation, and do a partial alignment at cycle level, and discard the errors using a QMUL clustering, and then get the swara samples out of this. So, I mean, we get near perfect results for Varnam dataset like expected, since it is one composition per raga. But in the Kriti dataset, we see that context-based performing even better than the phrase-aligned approach, and we know the reasons for that. So phrase-aligned approach works only with the data that it has access to, which is basically the number of cycles that it aligns, and that's very less as 20 to 30% in most cases. So that's the reason why context-based approach here performs better than the phrase-aligned approach. And this result is published in SMC 2016. So these results somehow validate that the Swara representation that we have developed is on par with what we can get as ground truth from these annotations and the phrase alignments. So, and to musically validate it, we have plotted these swaras across different ragas and have shown them to artists, and they validate that the distributions are representative of what they would expect in terms of the swara distributions in them. So here we show all the swaras of a particular raga, and we can see that this last one is the context-based approach, and this is the Varnam annotations, and this is from the phrase alignment. So we can see that the context-based either aligns with phrase aligned or semi-automatic in most cases. So yeah, it derives the same peaks and the similar distribution of pitches. So as a summary, so here we validated musically and quantitatively our swara representation that we developed, and there are certain limitations to phrase aligned approach that could have been improved to get more data from a given pitch contour, and some of them are that it relies on average tempo that we got from Varnam dataset, which can be a step in itself to estimate the tempo and then do the alignment. Here out of the 3 speeds, we have aligned only 1 speed. That's already 1:3 data lost. And the other one is, it can only use aligned portion, and that's a limitation of data. And as we can see, the context-based approach performed similar to phrase-aligned approach. But the advantage of context-based approach is it just uses the swara information of a raga. It doesn't use the score or symbolic notations. Yeah, and we musically validated the representations. And future steps in this direction would be, so we started with looking at swara as a probabilistic phenomenon, and clearly there are temporal and aggregate approaches to handle that. And we took an aggregate approach. And there are limitations to this, because though we would have liked to include more melodic and temporal context, the approach itself is constrained in some way. So, and we need, as a result, we need additional data from different sources like swara information or symbolic notations. And then its use in real-time applications is quite limited for this reason. But there are challenges with temporal approaches, and Gulati's work clarifies how varying a particular class of phrases can be. And this intra-class variability is something that would be challenging to develop a representation that can be abstracted in a higher level information. And we have developed a Saraga dataset that has phrase level annotations, and this we think is a good starting point to explore it temporally. So with that, we complete the second part. And in the third part, we will go through the ontologies that are created and the design choices. And then we look at the knowledge base population. So this is a more formal definition of ontologies, where it is said to be a manifestation of a shared understanding between different agents. And the purpose of developing an ontology is accurate and effective communications. And basically, these are the principles that they should adhere to. And so the scope of this work is constrained by our data sources, which are basically these, and the information that we extract from it, and primarily the applications that we have in mind for the knowledge base, which is data navigation and similarity. So let's start with raga ontology. These are the list of all the ragas and all the swaras in the raga and their symbols. Some of these swaras are termed as discordant or vivadi, and others are natural. And these discordant swaras are vivadi with a particular swara. So for example, Re3 is discordant with Ga2. And then there are these functions that the swaras play in the raga, like a swara that can be allowed to pause in the raga, and swara that frequently occurs in the beginning of the phrases, and so on and so forth. So these are the primary variants, and then each swara has three different variants, and these variants share these vivadi relations between each other. And also, so depending on the vivadi relation, we classify the swaras further into vivadi swara and natural swara. And these are the functional roles that the swara play in a given raga. And some of these can already be automatically extracted from the work in CompMusic. For example, the inferences from our swara representation can say if a swara is steadily sung or it's sung with gamaka. And there is another work by Gulati which identifies nyasa swaras, which are basically these pause points. And from our survey, we also have an approach to identify long steady regions in the pitch contour. So these can already be automated. And the next thing in the raga ontology is arohana and avarohana, which are basically ascending and descending ordered sequence of swaras. And based on these progressions, there are several classifications of ragas, like linear versus non-linear, where we identify a particular descent in ascending pattern or vice versa. And similarly, the other classifications are basically characteristics of these progressions. And noteworthy point is that these classifications are more theoretical, and some musicians dispute the relevance of these to phraseology-based ragas. And one of the challenges that we faced in modeling these progressions is to design order in owl. And so we have basically three options, and we have boiled down to this order list, since RDF sequence doesn't have any semantics associated and owl list is not available. And order list allows us to build some rules that we want to effect basically. And even the progression, though it is linked to swaras via order list, we also have contains swara because that allows classification schemes of the ragas. So this particular one classifies progression as a sampurna, which is complete progression, if it has at least one variant of all the swaras. And similarly, there are other class definitions and rules that we use in the ontology to effect these classification schemes. So next thing is these phrases and gamakas. Phrases are very similar to progressions, but also they have additional complexity that they have real performances. And for these real performances, we need a data model for abstraction. And linking this symbolic notation with real performance using segment ontology can partially address these. And gamakas, on the other hand, they are not defined as a sequence of swaras but melodic movements. So there is a high degree of variation which we can't account in ontology. And and so basically these are modeled, the gamaka is just belongs to a phrase without specific boundaries. And phrase is an order list. And in the thesis there is a slight mistake. So this should not be the case. This should be the case. And also the has phrase should point to the phrase. And so this is an ontology that we built for incorporating the swara representation into the ontology. And here we define a generic data model, which is about a manifestation of a musical concept. And we derive this pitch distribution subclass from that, and we create appropriate relations with raga and swaras for representing this model. And these are the three different component ontologies that we have for Carnatic music. And the first one is Tala ontology. I'll just directly go to the ontology. So Tala has two classes, basically Suladi and Chapu Talas. And it has three properties directly defined on the class, which are basically which determine the number of time units it takes, jati, and the speed it runs in, that's gati, and the number of beats it has. And Suladi Saptatalas are a specific form of talas which have also further structure defined on them, And for this structure, we also use order list to define that. And these are different types of forms. And so basically, these are not just the improvisatory and compositional parts are defined in the musicology, but in the interest of similarity and data navigation applications, we created four other form types: free flow, rhythmic, and lyrical and syllabic. So for example, alapana is a free flow kind of a form, and it's an improvisatory form. And viruddham is improvisatory and lyrical form, and swarakalpana is a rhythmic and syllabic form. So a form can be assigned to multiple classes. And another ontology that we defined is this performer ontology. And basically, we would like to say the performer is an artist performing a certain instrument and in a specific role. We were able to find design patterns that says performer is an artist and performing an instrument, but not in a specific role. That's the reason we defined another class and created this ontology. And this is the summary of the Carnatic music ontology and how they fit in, how the component ontologies fit into the whole picture. So we have created raga and Carnatic music component ontologies, and so some of the definitions of these classes are embedded into the class definitions in the ontology using OWL constructs, and some which we cannot do were specified as rules outside the ontology. And we found the representation of sequential information in OWL to be quite a limiting factor. And another aspect is this backward compatibility aspect. So as semantic web technologies are rapidly changing, we change our ontology to adapt to them, and that breaks the things that are previously published. So there is no solution as of now, except people recommend versioning, but that itself is a tremendous effort. And so with that, we complete the ontologies part. And so now we go to how we incorporated all this information and what's the size of the knowledge base that we have generated. So this is the editorial metadata that we have curated on Music Brains. It's a huge effort that many of us took part in, and so it includes big numbers like, for example, the relations between artists and recordings and concerts is of the scale of 10,000. So. And we take that and initially import it to Dunia, which is the browsing navigation platform that we developed. And we verify the data and consolidate it, and then map the schema of the relevant concepts that we work with, and map it with the ontology, and then publish it as a knowledge base, which we then link with the DBpedia, which is the primary source that we link these information with. Some of them are linked with URIs, which are implicit, and some of them are linked using DBpedia Spotlight. And so we found that, so describing so we used a lot of music ontology concepts and relations in the ontology, and we found this to be a limiting factor. Maybe I can hear more about this. So there is a music creation workflow between a recording and the actual track. And this, in our case, in most cases of the CDs, is not well defined, and this results in a lot of blank notes. And this is the reason we have defined some super relations, which are basically property chains of the existing relations. And also the semi-structured information that we haven't yet talked about is mainly about the ragas and the constituents for us, and basically their progressions and the musicological information. We got this, we created scripts to crawl the web and get this information from relevant sources, and we published it. So this amount to closely the semi-structured information, which is quite important part, amounts to almost 10,000 triples, and the metadata itself amounts to 73,000 triples. And so we ran our context-based intonation description approach for the entire corpus of CompMusic. we could only run for 2,338 recordings and 161 ragas, despite there are many recordings with just many ragas with one recording in them. And we could not get information for all of them. And we ran it for just the middle octave in the contour. And these are the parameters that we represented. And this comes to around 70,000 triples. So some of this work has been integrated into Dunia. So to navigate between recordings and concerts, finding similar recordings or similar concerts. And this representation of Swara representation is being used in Saraga, albeit an old one. So we have developed a representation that clearly shows like what swaras occupy what contour roughly. So, and in Riyaz, there is a huge potential for this kind of a knowledge base, mostly because we are now getting this user context information, and that seems to be a lot more potential for integration into knowledge base. And these are the overall contributions from the thesis. The first one is novel approaches for Swara intonation description, and we showed that it performs as good or better than the phrase-aligned data. And we developed a representation that facilitates high-level description for using with ontologies. And of course, we published these Varnam and Kriti datasets, which have machine-readable scores in them. And the second part is where we created ontologies and knowledge base for Carnatic music, albeit a beginning one. And there we described these Swara progression, phrase, and raga classes, and other component ontologies for Carnatic music. And we also proposed a data model as a generic class to encapsulate all the descriptions that arise out of audio music recordings. And we have throughout highlighted some limitations and challenges in building a multimodal knowledge base for a music tradition. And these are other contributions which we did not talk about, which are in thesis. And so evaluation framework and guidelines for open information extraction systems for ontologization of a thematic domain like Carnatic music. And we proposed a distance measure for semantic web data, and along with an approach that takes out the salient aspects of a music tradition given a text corpus. And these are the publications that came out of this work. And these are other contributions that are collaborations with other researchers. So, as we said, the future course of this work for intonation description is more exploring towards exploring the temporal aspects of the Swara intonation. And as per the rest of the parts of the thesis, it's mainly combining information extraction with ontologies. Since these thematic domains usually have limited vocabulary that can be seen as an advantage, and the information extraction technologies themselves can be primed with these vocabulary so that they perform better. Right now, the recall rate of the open information extraction systems used on this limited data is quite appalling. So, and the next step would be when developing applications that take advantage of this knowledge base. Like I said, Riyaz is a very potential application for that. And as for me, I will continue with Music Muni Labs, which is a spin-off from MTG, and that's where I work on Riyaz. Thank you.
Thank you very much.